Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Douglas Comer, who is a professor of computer science at Purdue University. He was the chair of DARPA's Distributed Systems Architecture Board. Professor Comer has written a series of best-selling technical books on the internet and computer networks, operating systems, and computer architecture. He is also a member of the Internet Hall of Fame. Welcome, Doug.
Thank you.
I want to start with one of your earlier papers entitled DcNet, a data center network architecture that supports live VM migration. VM stands for virtual machine, in which you say as more enterprise applications are hosted by VMs in the cloud, a significant amount of network communication occurs among servers within a data center, increasing so-called east-west communication. In addition to scaling to accommodate more east-west traffic, future data center networks must support efficient VM migration, which is used to optimize power consumption. So in this paper, you're proposing a new data center network architecture called DcNet. Before we get into it, Doug, I want to do a level set regarding the cloud. The cloud has been quite popular in this decade, I would say. Lately, most startup companies and small companies don't even keep a computing infrastructure on their own. They work from the cloud entirely. And larger companies have moved into sort of their own private cloud infrastructure. In the public cloud arena, Amazon popularized their AWS cloud. Now they have a lot of competition from Microsoft Azure, IBM Cloud, and Google Cloud. And so it seems like it's getting more and more popular. For everybody to get a general understanding, could you talk a bit about sort of the evolution of the cloud and where we are today?
Okay, well, let's see. You're right that it started way back in around 2000. The real motivation for the cloud was pretty simple. We ran out of the ability to build larger and larger, faster and faster single individual processors.
Yeah.
And eventually we hit a power wall. Couldn't make them go faster. Actually, the speed of a processor and the power consumption are related in a funny way. The power consumption goes up as the square of the speed. So as processors got faster and faster, power consumption went way up. And eventually it got to the point where so much power was being pushed through a single processor that they couldn't go faster without burning out the chip.
Yeah.
So we end up with the need for parallelism. That's how we ended up with multiple cores. Instead of one processor, you get multiple cores, which are really just copies of a processor. And then by around 2000, it became obvious that an individual processor with multiple cores wouldn't be enough. We needed to have multiple processors.
Hmm.
So that's where the cloud comes in. Cloud idea was, why don't we take a whole bunch of computers, each of which are probably multi-core, big memory machines,
Yeah.
put them in one place and find a way to take processing and put it on this new architecture.
Ironically, Doug, it's sort of coming full circle, right? I remember in engineering school, when I was going to school in India, I used to work on IBM 370 mainframe. And then we went into sort of distributed computing for a while, and then cloud is sort of bringing it back in a sort of centralized computing architecture, right?
That's absolutely right. In fact, I'm writing a new book on cloud computing, and you will find that exact statement. that we spent a long time moving toward a distributed environment where we got smaller and smaller computers in the hands of individuals. And we ended up with this hugely distributed environment. And then all of a sudden, cloud comes along and it really says, we're going to centralize things.
Right.
One of the ironies is it used to be called a computing center, and now it's called a data center.
Right.
And that makes all the difference, because computing center is a bad idea, but
right.
Data center is a good idea. And if you look at the infrastructure, it's really ironic that they're using raised floor with the coolant going underneath the floor, just like an old computing center. It's the same old technology from the 60s. But
yeah. So I know that, that we'll talk a little bit about, the big cloud providers like Amazon and Microsoft, but also large companies like Pfizer or Boeing or somebody like that have sort of their own cloud, right? They have data centers spread around the world. Is that how they do it?
Well, if you went back 5 to 8 years, you'd be right. Every company was building their own private cloud. They were taking all the infrastructure. So a large enterprise company would move all of its servers out of individual departments, which is what the distributed world was. Every department had their own servers, put them in a centralized data center and call it a private cloud. They would use the same technology as Google and Amazon and, the same cloud infrastructure technology, but they would do it all on their own premises. But if you go talk to the big companies now, places like Walmart, FedEx, you mentioned Pfizer, go on down the list. In fact, almost all of them are now moving to a hybrid cloud. They are renting space in the public cloud in Amazon or Azure or Google Cloud, and they also have some private cloud stuff. But more and more, they're moving the sort of, I don't know what you'd call it, pedestrian computing to the public cloud and using their private cloud only for specialized things. For example, if you're in healthcare, you may need to keep certain records HIPAA compliant. You don't want to move them to a public cloud.
Right. So only for security and privacy reasons, if they need to keep some data, they seem to have some sort of a privatized form of it. So if they are doing that, Doug, are we on a path? So there is scale, huge amount of scale in this business for Amazon and Microsoft. So a large company is saying, the per unit cost of compute and storage is going to be lower by going to the public cloud, and hence strategically, ultimately, they're going to do that anyway, unless they have a need for some sort of privacy, security, data storage.
Right. Well, there's two sides of the coin. One side of the coin is all the cloud providers are telling everyone, hey, we get quantity discounts. And we get such quantity discounts that you can't get. These the big cloud providers are called hyperscalers. I don't know if you've heard that term, but they are so big that they are far beyond what any organization is. And And if you go to some of the organizations and look at their infrastructure, you'd be amazed. For example, think about an organization like Walmart.
Yeah.
Think about an organization like Bank of America. Every ATM is on the Bank of America network. That's huge. And yet, the big hyperscalers have even more infrastructure. So they get bigger discounts. And they also claim that they amortize the cost of training over many customers. So the Amazons of the world, AWS and Azure, they each have multiple tenants in their data center. And they're saying, look, the reason we're so cheap is, yeah, you need somebody who is a real expert on, pick a topic, Oracle database configuration, debugging, all of the things about Oracle databases. Well, we have that expertise, but you don't have to pay for it all yourself. We'll just charge you a small fraction because our experts are shared among all of our tenants. And we have hundreds or thousands of tenants. So it looks like they really win on economics. But the other side of the coin, is they're trying to lock in customers.
The switching costs are quite high. So once you get them, you have to continue, right?
Yes, they're working very hard to make it easy to get in. It's like my mother used to say about trouble. Trouble is easy to get in, and it's really hard to get out.
Right. But do you see, is it an advantage from a business interruption perspective? So if you think about AWS, obviously they have a very large, redundant infrastructure around the world. Any single company trying to replicate that will be too expensive. So is that true that they're providing additional advantages in terms of a business interruption issue for a large company?
Oh, they have. If you go to the large cloud providers, you can find a long list of services they provide that would be very hard for you to do in an enterprise outside of that.
Yeah.
They start with things like security. How about backups? They have really nice backup schemes where they transport your data to a faraway place. They keep multiple copies. They do it all automatically. It's really hard for you to, if you're an enterprise, how are you going to lease space in some storage facility far away?
Yeah. And the flexibility they offer, this may not be a big deal for large companies, but small to medium-sized companies, their compute requirements might be quite volatile. And so, in some sense, you can get, high compute when you need it, and then, sort of turn it off if you don't need it, right?
Oh, exactly. In fact, that notion of elastic computing where you can pay for what you need is central to cloud. But beyond that, we talked about the hybrid cloud with a private cloud and a public cloud.
Yeah. Another
reason for having hybrid cloud is economics. Suppose you're a company that has very seasonal business. Let's take, tax returns. I assume that's a seasonal. I'm not a tax return guy, but I assume that's really seasonal. And on April 1st through April 15th, they will be processing zillions of tax returns, and they're going to need extra capacity.
Yeah.
But it's foolish to buy the extra capacity and leave it idle all year. With a hybrid cloud, you can scale your local cloud, your private cloud, to handle the average case. And then, come April 1, just start leasing space in the public cloud and pushing some of your load out there.
Right.
And you can expand as much as you want. And by the way, the large cloud providers provide this wonderful service. You'll be surprised. They make it really easy for you to run the same software in your private cloud, and they'll almost give it to you so that you can then, transfer to their public cloud easily.
Right. Yeah, so let's talk about DcNet a bit. And so when you have a cloud infrastructure, you have data centers in different geographical locations physically. So you have clusters of processors and storage space kind of distributed, and there is a lot of data shuttling back and forth between these data centers, right? That's one of the issues.
Well, the first issue is, and the inner data center is one thing to think about, but the big issue is that there's a lot of intra data center traffic moving around. An organization moves its compute to a data center. Let's suppose it picks one in, I don't know where, Oregon.
Yeah.
And it moves its computing to that data center. It probably has I don't know, a payroll database, an employee database. It probably has a accounts receivable database. And now it's doing all of its processing. And of course, when you do things like payroll, well, you have to talk to the employee database, and you may have to talk to accounts receivable or accounts payable to do billing for things. And all of that traffic running back and forth among servers that are actually owned by the same organization, all of that is called east-west traffic.
Okay.
And that's the first big change that happened in data centers. Early data centers were all about web traffic. You know, there was a user out on the web and it came into a web server. And so a company had 10 zillion web servers, and when traffic came in, there was a load balancer that split up the load among the 10 zillion web servers, and that was it. All the traffic came in from the internet to a web server and back out.
Right.
But with cloud computing, that was one of the big changes. Suddenly, instead of architecting a data center to handle traffic coming in from the internet and going out, the cloud people had to handle traffic moving from one server inside a data center to another server owned by the same or run by for the same tenant.
Okay.
Back and forth. So
let me ask a quick question, Doug. So I don't know much about this. So for a company that's moving to the cloud, let's say Amazon AWS, is there any advantage from sort of co-locating? Let's say they have different compute requirements. Can they actually co-locate those compute requirements close together? Would that make a difference from a data traffic perspective?
Oh, that would have been a great research question in 2010. There have been 4,000 papers published about how to do placement of a tenant's computing within a data center to minimize latency, network traffic, server access, and by the way, storage is usually separate from the servers inside a data center, so storage access.
Okay. So that problem has been solved. So there's
no. That problem is well known. There are lots of ways to optimize things. It is one of those multivariate optimization problems that will never be solved. You cannot possibly. In fact, imagine, some company comes along and it wants to do cloud computing. Yeah. And maybe what they do is they have lots and lots of little applications talking to files. So there's storage on one side of the data center and there's all these little applications. So that company wants to optimize application to storage. And then there's another company that's doing, financial services. And those guys want to minimize network latency. So they want to put their stuff closer. And you get all of these optimizations. Do we want to optimize the network traffic, total volume, the network latency? Do we want to optimize storage access? Do we want to optimize the placement of, an Oracle database so that you can get to it faster? There are 1,000 possibilities for optimization, you see?
Yeah.
Depending on the company and what they're doing.
Right. So is that something that DcNet is tackling, or say a little bit about what DcNet is and why is it important?
Well, let's start with how data center networking evolved. I told you it started with web service with a hierarchy of coming in and going out to the internet.
Yeah.
Then we changed, and a new architecture called leaf spine was invented. Leaf spine is a wonderful little architecture. It's scalable, and it handles east-west traffic pretty well. In all of this, that's just sort of the wires. How do you connect them? And there's an architecture for connecting them. You can find that in my forthcoming book. But the interesting question is, what protocols do you run on top? And it's the internet protocol. Everybody is using IP throughout the data center. Okay, how does IP work? That means every switch in the data center, and data center networks are wires connecting switches.
Yeah.
So every switch has to forward IP packets, internet protocol packets. And here's the problem now. If I had a static network, IP works extremely well. Static in the sense that you tell me where all the computers are. You give each computer an address. I configure every switch to know where the computers are and know how to send packets to the switch and to the computer, and we're done.
So that's sort of like a typical router switch.
Exactly. An old routed network, the way it was done in enterprises.
Yeah.
When you put a server in a company, it used to go into a particular department, and you knew where the server was. It had an IP address, and it always stayed in the same spot.
Right.
So configure the network throughout the enterprise so that if anybody wanted to reach that server, all of the routers and switches would know exactly how to forward packets to get there and to get back. And that never changed. But now we move to a data center.
Right.
Here's the interesting thing about a data center. Data centers are not static. Instead of having fixed computers with IP addresses, what we have in data centers are virtualized servers, either VMs, virtual machines, or containers. Each VM or each container gets an IP address, and containers and VMs can be placed anywhere. And here's the punchline, they can be moved.
Right.
Now, why would you move a virtual machine? Well, data center people want to move all the tenants' virtual machines to places that are close by to minimize, as we talked about, things like network latency. They want to put it near the storage that particular tenant is using. But things change over time, More tenants come in, you start allocating tenants to servers, and then one day you realize, what we really need to do is we've got this particular tenant needs more virtual machines, and all the servers near where this tenant has their virtual machines are in use.
So there's sort of a global optimization being done sort of dynamically, right? As more tenants come in or tenants go out or requirements change,
yes,
there is sort of a global optimization that they need to do, which would mean that the VMs and the containers are going to move around in that environment.
Exactly. And remember, we talked about elastic computing, where a company can say, by the way, folks, now today I need 200 more VMs. Please spin them up. And then tomorrow they can say, I need 300 fewer VMs.
Yeah.
So that's that dynamic of VMs coming and going. With containers, it's even faster. VMs usually take a minute or more to spin up, but containers can be spun up in hundreds of milliseconds, tens of milliseconds. So that dynamic means suddenly we have IP addresses moving around, changing, popping up, going away.
Right.
And now we need a network that can adapt quickly. Well, go back to the old style of IP networking. And if you've ever read any of my books, you know that we have invented routing protocols, and people use routing protocols that handle dynamic routing. When a new address pops up, a routing protocol will forward that information to all of the routers and switches so that that address is known and how to reach it is known.
Hmm.
But routing protocols take a long time.
Hmm.
They do not converge as quickly as containers come and go.
Hmm.
So now we need a network that can handle this really rapid change. And that's where DcNet came in. I started asking myself, how can you handle that rapid change? Well, one of my colleagues suggested what we really need is a routing protocol that converges quickly. We just send routing information around much faster. Maybe we need a special high-speed network to send just the routing information.
Yeah. And so is it sort of a lookup table, Doug? So what exactly, how exactly is it done?
All right. Inside every router or switch, there is an IP forwarding table.
Yeah.
The IP forwarding table has a list of destinations, that is to say, IP addresses, and a next hop on how to reach them. Which next switch? Remember, the switches are all connected with wires. Mm-hmm. I'll say switch. There are routers and data centers, but almost everything is switches. Right. So let's just think about it's the same technology with slight modification, but let's just think about a switch as a box, and it has this forwarding table in it that says which connection, which physical wire to go out to get to a particular destination.
Yeah.
And then the next switch along the path has another table in it that says which wire to go out of there to reach the destination. Mm-hmm. And routing protocols run in all these switches so that when a new destination appears, all the routing protocols, think of them as running programs that talk to one another.
Yeah.
They exchange the information and a network, let's say a host appears over on switch one. Mm-hmm. The routing protocol detects it. Hey, there's a new connection here. I've got a destination. I've got a new destination that nobody knows about, and I'll tell all my neighbors. So it tells the routing protocol software in all the neighboring switches.
And that takes time.
Yes.
Yeah. And so the goal is to reduce that time, right?
Well, that's what my colleague said. He said, maybe we could find a way to just reduce the time, still use the same approach, but reduce the time. And I thought about it, and I thought, we have worked on routing protocols now for 40 years. I don't think they're going to get a whole lot faster. But there may be a better way. What if we used a completely different approach? Mm-hmm. What if, instead of propagating information about every IP address and how to reach it, what if we gave a number to every switch in the data center? In particular, we gave one to every switch that's in a rack. In a data center, computers are collected together in racks. So there's a whole bunch of these server computers in a rack, and there's a switch in the rack called a top of rack switch, usually because it's physically located at the top. Mm-hmm. And that switch connects all the servers in that rack. So what if we gave essentially every rack a unique number?
Like a MAC number?
Well, for right now, let's just make up a new number.
Okay.
So we make up a new number, and we give this number to every switch. Mm-hmm. And now, if I had that, I could build forwarding tables in all the switches that use these numbers to get to the appropriate rack. If I knew when I was given a packet which rack it was in, then I wouldn't have to change all of those forwarding tables all the time. Mm-hmm. But I would have to change the binding between where a computer is, where an IP address is, and which rack it's in.
Yeah.
And that can be done much faster. That's what DcNet does. What it really does is it says, okay, when a new container appears, or when a new VM appears or when a VM moves, here's what we're going to do. That VM has an IP address, and we are going to find out the new rack number, and we're going to do a binding, a tuple that has the IP address of the VM and the rack number that that VM is now in. And we're going to tell everybody where that is. And we're going to propagate that information to every top of rack switch. Now, that information is actually really pretty small. It's just two numbers.
Right.
It can be done quickly.
And the address of the top of the rack switch is static. That doesn't change?
Yes. The number that we assign, and you said address, and in fact, what DcNet proposes to do is misuse the MAC address.
Yeah.
So we're going to take the MAC address and reinterpret it. It doesn't have to be a MAC address, but that's really convenient because we can do all of our work with no new hardware.
Right.
We steal the MAC address, assign a unique number to each rack, and now we can route to that rack by looking at that number without worrying about IP addresses anymore.
Yeah, so if I understand this correctly, Doug, so let's say I have, on rack 2, I have a new container show up. Now that container has a new IP, but I can get the packet to that rack 2 very quickly because that is static. That number hasn't changed. But once the packet is to the switch, then it just has to find the new IP for that container. So it's sort of a last mile problem type thing.
Once the packet reaches the top of rack switch, here's another little trick we do. We actually tack an extra few bits onto the number so that the prefix tells you the rack. I told you every rack gets a unique number. Well, in fact, every server actually gets a unique number, and the prefix of the number is the same for all the servers in the same rack. Okay. It's the rack number. So what we do is, way over on the other side of the network, somebody wants to send a packet to this new container. Mm-hmm. Somehow it has to know the IP address of the container, and that's all just standard networking. In order to send a packet, you need the IP address of the destination. So you get that, and then we do a binding on the outgoing packet. We do a binding that maps the IP address of the destination to this magic number, which is really a rack number with a few extra bits to tell the server in the rack. Send the packet across the network looking only at that magic number. Yeah. And all of the forwarding in the whole network is completely static. It's been built in. We know where rack 2 is, so just look at the prefix, find the rack number, go to it. When the top of rack switch on rack 2 gets that, it looks at the packet and says, oh, the rack number here, the prefix of this MAC address is me. Right. I take the next bits, figure out which server in my rack should get this, and send the packet to that server. Okay. Now the server gets it, and that's where the server says, okay, this packet has reached its final destination. I can use the IP address in the packet, because it's a regular old packet with a regular old IP datagram in it. I can use that to figure out which application or which virtual machine or which container on my server should receive that packet.
And so in all the inbound traffic, there is no need for an IP destination.
There's no need until you get to the final server, and that's how you look at the IP destination.
Okay. So is this being done in the large systems like AWS or Azure?
Unfortunately, it's still an ongoing research project. We have DARPA funding. We are working on a prototype. As you can imagine, COVID has had a very dampening effect. We've been locked out of the lab for 6 months. We weren't supposed to go work in the lab. So it's had a bad effect, but we hope that it will come to people's attention soon.
Yeah. It seems like it's something that is sorely needed. So it will ultimately, if you are successful, it will have both a speed latency effect as well as sort of cost effect, because you can reduce a lot of the complications of spinning up and spinning out containers. Sounds right?
Yeah, it'll make a whole bunch of things faster, but everything you can do in a data center to reduce things like the cost of creating and the cost of tearing down machines and virtual machines and containers is important. So yes, that'll help a lot.
Okay. I want to jump into another paper that you have, Doug. This is entitled Towards Disaggregating the SDN Control Plane. SDN is Software-Defined Networking. You said current SDN controllers have been designed based on a monolithic approach that integrates all of the services and applications into a single huge program. And this monolithic design of SDN controllers restricts programmers who build management applications to the specific programming interfaces and services that a given SDN control provides, making application development dependent on the controller, and thereby restricting portability of management applications across controllers. So this is sort of a very rigid infrastructure, and you have an idea to make that much more open and flexible. Is that the idea?
All right. Well, there are two things going on.
Yeah.
So let's start with the software engineering aspect. We started using controllers in our SDN experiments, or in the DcNet experiment, for example. We are trying to figure out how to use controllers to configure the SDN switches. All of the switches in a data center are configured with software-defined networking. So we started with our experiments, and we started with Open Daylight and the Open Network Operating System, ONOS. Those are two controllers that have been popular, and we were shocked. ONOS, for example, was a huge program. I say huge, and I said that in the paper, and I don't tend to exaggerate.
Yeah.
Here's what we found. ONOS had over 180 services that it supplied that you could use you wrote applications, and you talked to this SDN controller, and the SDN controller would configure switches for you. The idea was you were supposed to write high-level applications, things like, please block all, incoming packets from this port.
Yeah.
And it would configure the firewall automatically. Or please route all packets headed toward this particular destination out of the data center. And it would handle all the routing. So we have this picture of high-level application talking to SDN controller, and SDN controller talking to switches to configure them. And that's low-level details, making sure all of the forwarding tables in the switches do what you want it to do.
Yeah.
Okay, so the high-level application can do all sorts of requests, and that's very nice. But the SDN controller, the way it was built, had 180 major pieces in it. And it was compiled and linked as one giant program.
Okay.
If you're a software engineer, you immediately see the disadvantage here. Suppose I want to change one of those little services, a minor change. I want to add an argument, the only way to do it is to make the change and then recompile and relink the entire ONOS controller. That seems like a really dumb architecture just from a software engineering point of view.
Right.
That's step one. On the other hand, there's another whole situation that you have to contend with. If you look at the cloud, and you look at cloud native software, it is not done the same way that you did things in the old days on a server that ran in an enterprise. The enterprise servers ran on a single computer. Each department ran a little server. They ran a copy of the server software. And if you needed to handle multiple clients, well, it was only a department-wide server. So, well, you just use concurrent threads or concurrent processes. Not a big deal.
Yeah.
Now we get to the cloud. And you want to run something in the cloud. How do you build cloud native software that scales? Suddenly, if you go to the cloud, you're not talking about 4 or 5 connections coming into a service at a given time. You're talking about thousands or maybe tens of thousands.
Yeah.
The way to scale it is to scale across multiple physical servers. That is to say, you either run containers or VMs, and you run 10,000 containers, each of them spread out on many, you don't put them all on one physical server, you spread them out. So they're spread out throughout the data center, and you can scale up. And if a particular server becomes overloaded, well, you don't start more on that one. You wait for those containers to die, and you start them on lightly loaded servers.
Yeah.
Okay, so that's scaling in a data center. Now let's take Onos and ask, it's a controller. It's going to be running in a data center. Shouldn't you be able to scale it? Well, of course you should. Because, if you look at data centers, they don't have 5 switches or 10 switches or even 50 switches like we have in our little test bed at Purdue, our lab. They have tens of thousands of racks.
Yeah.
So you can't have one copy of Onos serving tens of thousands of racks. You have to have multiple copies. We have to be able to scale it, and we need to be able to scale it by making these copies on multiple physical servers so we can spread the load.
Right.
Good. Now, how do we take a monolithic architecture, the way Onos was designed and built, gigantic, huge, single piece of software, and scale it? You can't.
Right.
What you need to do is what the cloud native software designers call microservices.
Right.
Microservices means you take a big application that you want to put in the cloud, you divide it into small pieces, you run each piece independently as a container or as a VM. Let's just think about containers. It's the easiest way to do it. We'll run each piece as a container. And now when you want to scale, you just create copies of the container. Right. And if you do that, the beauty of it is, suppose that an application has, 5 pieces. Suppose that one of them is hardly ever used.
Yeah.
The second one is used all the time. The third one is moderate. The fourth one's used all the time. And the fifth one is by far the big winner. It has more hits than any other piece. By breaking it into 5 microservices, you can run them in containers. And the fifth one, the one that's going to have to scale the most, you just create the most containers for it.
Right.
Lots and lots of containers.
And give it more resources. So
you give it more resources, and there are load balancers that'll balance the load among all of the containers so that every time a new client comes along and does a request, it goes to either a new container or it goes to a lightly loaded place. It's very nice. It's all automatic. And that architecture is the architecture we proposed for Onos. So look, an SDN controller is an application. It runs in the cloud. It ought to be structured the way cloud native software can be structured. So they can be expanded.
So in that case, Doug, you take that and you basically split them into 100 different microservices, and all of them basically running independently. So if you need to change one, you just have to worry about that one, right? Not the
Exactly.
entire thing. Yeah.
Exactly. One of the big arguments for microservices is you can go in, decide that you're going to change a particular service. Of course, if other services are using it, you have to make your change backward compatible.
Mm.
Maybe you add an argument or add a possibility somehow, but you leave backward compatibility, make the change, reboot the service, and there are lots of technologies for restarting the service. You can read about them in my book. And you don't have to change everything. You can change one microservice at a time.
And you could, I don't know much about this, Doug, but I'm just asking the question. So these services could be agnostic if they are sort of RESTful services that could be consumed by pretty much anything.
Okay, now we get to the question of what should the interface be? And that's one of the things that we explored in our paper.
Yeah.
And the RESTful interface, the good old-fashioned web interface with HTTP and making nice little HTTP requests, get and put, that works fine. But when you start to scale up, there are some problems.
Mm-hmm.
And Google has explored alternatives, gRPC, for example. And one of the things that they noted is you may want to have not just a request response protocol. The good old-fashioned RESTful interface is request response. It was based on web pages.
Yeah.
I make a request, you send me a web page. Then I make another request and you send me a different web page.
Right.
But for microservices, maybe what you need is you need to get a lot of data. So I make a request and you pipe me, I don't know, an entire file. Or better yet, you do some processing on data and pipe me a whole bunch of data.
Mm-hmm.
Well, the RESTful interface isn't really set up for that.
Right.
So we concluded after looking at performance, capability, functionality, that an interface closer to gRPC, whether you like that particular version or not, we happen to like it, but a gRPC-like interface is superior.
What does gRPC stand for?
Generalized Remote Procedure Call.
Okay.
Remote Procedure Call has been around for many decades, going back to the 1980s.
Right, right.
One of the fun things is we have students coming into computer science who have never heard of Remote Procedure Call, and then they get to the cloud class and they're learning about gRPC, and for them it's all the first time. And I have to tell them, no, folks, this is really old.
Yeah, almost everything in computer science, Doug, seems like we are coming full circle.
Exactly, right. We mentioned already that we're going back to a centralized model, and now you want to know what's really funny?
Yeah. There's
a new research effort called edge computing.
Right.
And guess what edge computing does? It says, hey, you've concentrated everything into a big centralized data center. That's a bad idea. What you really need to do is you have little tiny data centers all around close to where individuals are using it, and do as much processing out there as possible, and then use the centralized data center for the rest. In other words, let's have a distributed cloud. After the cloud guys preach centralization, centralized, now they're preaching, hey, decentralize.
Yeah, it's it keeps the field interesting, to say the least. So Doug, in conclusion, if you look forward 5 years, I know there are some constraints that some of them we discussed already from the growth of the cloud. From a business perspective, it appears the direction for most businesses. From a technology perspective, what do you see, say, 5 years from now? How will the whole cloud business evolve?
Well, there are two things that I'll say. Um, the compute guys will get faster and bigger, and the memories will get larger, and all that stuff. That's boring, and it'll keep going.
Yeah.
The big crunch, and I don't know. I'm not really in this part of the research space, but the big crunch seems to be not can we do computing resources? Can we do storage resources? Can we do networking resources? That's not the question. Yeah, those are evolving. We'll be able to do things. But there is the question of power and cooling.
Right.
Everybody in my classes, all my computer science students think that's really boring, but I have to tell you that power dominates everyone's thinking in the cloud right now.
Yeah, northern Sweden has a very large number of data centers.
Yeah.
Just for cooling. Yeah.
So there's the requirements. You can't place a data center, a large data center, unless you can get enough power. Go to a power company and say, hey, I'd like to put up a building here. And by the way, folks, I'm going to need 25 gigawatts. Can you deliver that?
Mm.
I'm going to need as much as a small town or as much as a medium-sized town.
Unless the edge computing, as you say, really takes off again.
But even with edge computing,
yeah,
that adds to the problem because now we need to have cooling. So once you get power, then you need to have cooling.
Mm.
By the way, there are predictions that by 2025, 5 years out, data centers will consume almost 30% of the power on the planet.
Right.
If we keep building data centers the way we are, and of course, when you talk to the 5G guys doing 5G phone networks, they want to put edge computing, that is to say, miniature data centers, first in every cell tower, second in every regional place around the world, so they have regions with cells in them. That's going to be a lot more computing, a lot more data centers. They're tiny, but there's the fact that there's so many of them. Think about cell networks and how many computing facilities you'd need to have one first in every cell tower and second then in every region and every larger area.
Yeah, so that's also point to maybe we need a major innovation in hardware design. So, there's some talks about memristor-based computing, really fundamentally change the power requirement equation in computing. It seems to me that if we are going to consume with the status quo technology 30% of the power generated, that seems like an unsustainable design into the future.
Yeah. But it's not just, individual devices. It's not just, it is consumer demand. Businesses want it. Consumers want it. Everybody wants cloud. So,
yeah. So do you see, Doug, any sort of, there was some talk about quantum computing, any sort of fundamental change in the hardware aspect of compute?
Are there fundamentals coming? Well, as you pointed out, there are lots of people doing research on how to optimize power in whatever, how to increase battery life, how to on and on and on. So power is a big thing. And everything from individual transistors, the solid state physics people figuring out how to minimize power there, to large scale cooling, how to do better cooling. Yeah, there are lots of things. Are there any fundamentals coming? I don't know. It's hard for me to predict.
Yeah.
I'm sure that someday we'll wake up and somebody will say, hey, we can do things with less power.
Yeah, nothing much has happened, right? If you look at last 10 years, I don't think we have changed much from a hardware design perspective, right?
Well, if you talk to chip manufacturers, they are certainly doing some crazy stuff with vertical transistors and squeezing more transistors in a space by moving vertically. That's crazy. So there's
Yeah.
there's some stuff that's going on down there. The other side that always tickles me is we have become used to having sloppy software because the hardware makes up for it.
Right, right.
And
That has ended. Yeah.
and there's another way that we could go about doing things much better. We could build much better software that somehow didn't just slop so much into memory. Remember, every time you're using memory, you're using power.
Right, right. Yeah, so that's yeah, so there are two axes there. One is, sort of some big change in the hardware design, and the other is what you're suggesting is, yeah, because we got lazy last 10 years writing software because there was so much capacity. Maybe that regime has ended. Maybe we need to go back to really think about software design much more, much more efficient fashion.
Yeah, I just read an interesting study where someone had gone back and looked at software over the years and what computing power was available and what performance was achieved. And it's just amazing that we got such better performance out of really terrible hardware back in the 70s and 80s because everybody was working on optimizing the software.
Mm.
And then as things started to get faster and faster and bigger, software engineers got lazier and lazier.
Right. Yeah.
Yeah, in the 90s, for example, I had always worked on a VAX. VAX was a very early time-sharing system.
Yep.
I had
That was digital.
Digital Equipment Corporation. I had the BSD operating system running on a VAX. I had Corn Shell from David Korn. I had an editor from Jim Gosling. When he was a grad student, he wrote an editor at CMU and gave me a copy. And I loved it. It was Gosling Emacs. And I was using it. I was happy. And then in the 90s, students found out that I was working on a VAX and they said, that's a 1 megahertz machine. Are you crazy? We now have machines running at multiple hundreds of megahertz.
Right.
And you have a megabyte of main memory? That's insane. Oh, that's just tiny. So they convinced me, you should move to one of the computers that we have in the lab. It's an x86 running Linux, and the hardware was 2 orders of magnitude faster, 2 orders of magnitude bigger memory, 2 orders of magnitude faster bus.
Mm-hmm.
It was just tremendously better. I sat down, I brought up Emacs and started to edit, and I waited for it. And finally it popped up. And I tried again, and sure enough, it just took forever. I filed a trouble report with the IT staff saying, something is wrong with these new computers. I've been trying them, and it takes Emacs forever. Mm. And the IT guy came to me and said, well, Doug, you don't understand. You were still working on a VAX, and the software was really good back then. And yes, you type Emacs, and bang, the windows appear, just like that. But these students have been working on this horrible system for a long time. They're used to waiting. When they say Emacs and it takes, a second or two, that's life. That's the way they live.
Right. Yeah, it's sort of expectation. So this has been great, Doug. I hope COVID recedes and you get back into the Purdue labs and make DcNet work.
We are back in the labs this week, so everything should start working again. Thank you very much.
Yeah, thanks so much for spending time with me, and good luck with everything. Thank you.
Thank you. Bye.